we need to talk about fractions. So, let's see what we can say about fractions. So I'm going to give you a little bit of a word problem. It's not really a problem, just a sentence. Let's suppose I have a half of a dollar. Alright, so suppose I have a half of a dollar. That's 50 cents. That's one way to say it. I can say that by saying I have 1/2 of $1 is a half a dollar, which of course is 50 cents. I guess that's not a very interesting example. Let me say I have half of, say, $10. That's a little bit more interesting because then I have 1/2 of $10. So how many dollars do I have? I have $5. And I know this because, well, you know, half of $10 is $5, but in terms of the arithmetic, when you use the word of, what you're doing is multiplication. So here and here, we're doing multiplication. So knowing just that the word of translates to multiplication, that'll help you to translate a lot of times words into arithmetic, which is important when you do problem-solving types of things. Okay, so let me do a more interesting one. Suppose I have, let me come up with some good fractions. 2/5 of 3/4 of a dollar. Okay, so this is a little bit more challenging. So I'm going to write this down just like I did before. I have 2/5 of, so this is going to be multiplication. I'm going to multiply the 3/4 of a dollar by the 2/5. And how the heck much money is that, you wonder? Because it's not as obvious taking 2/5 of 3/4 of a dollar as it is taking 1/2 of $10, which is fairly straightforward. Now we can do this because we've all worked with money. So 3/4 of a dollar is 75 cents. A fifth of 75 cents would be 14.15, and so 2/5 is gonna end up being 30 cents. But I don't think that this is obvious. And what I need to do is I need to perform this multiplication. Two-fifths times 3/4. Now here I indicated multiplication just by setting the fraction next to a set of parentheses that held something that I wanted to multiply it by. So in mathematics there's a sort of a general rule where if you have two things like this 1/2 and this thing in parentheses sitting next to one another without any indication of an operation like a plus sign or a minus sign or a multiplication sign or a division sign, they're just sitting there next to one another, then it's understood to be multiplication. So I have to do this 2/5 times 3/4, and how do you do that? Well, there's one thing I'm going to have to ask you to take my word for about fractions, and then we'll get the rest of it from first principles. So when you multiply two fractions together, you go straight across the top and straight across the bottom. And so in order to do this, I would do 2 times 3 in the top, and 5 times 4 in the bottom, and 2 times 3 is 6, and 5 times 4 is 20. And so this is 6/20 of a dollar. Also not a tremendously informative number. 6/20 of a dollar. If you were in a store somewhere and they charged you 6/20 of a dollar, you probably wouldn't know what the heck they were talking about or how much money to give them without doing a little bit of arithmetic, at least in your head. So this is not a very nice number for a couple of reasons. The main reason is this fraction is what they call not reduced. Meaning that there's another nicer way to write that fraction. So reduced fractions are written in the nicest possible way, and if they're not reduced, then there is at least one nicer way. Depending on how unreduced they are, there might be really, really nice ways, or a lot of really nice ways to write the fraction. So what you do to reduce a fraction is you basically undo this multiplication, but you look for common factors in the top and the bottom. So you can get right down to a prime factorization. So 6 is 2 times 3. 20 is 2 times 10, which is itself 2 times 2 times 5. So I can do 2 times 2 times 5. Let me erase that. A little bit of scrap work here. So then you can look at this and you can look for common factors in the top and the bottom. So this, I can rewrite this fraction. So I'm again undoing this multiplication. So here I've multiplied two things in the top. And so I can write that as two fractions. 2 over something, and then 3 over something. I've multiplied three things in the bottom. I can put one of them here and two of them here, and multiply these two fractions together. So it looks like I've kind of gone around in a circle. I started with 2/5 times 3/4. I did the 2 times the 3 and got the 6. I did the 5 times the 4 and got the 20. And then I undid the multiplication. So multiplying and factoring are reverses of one another. Factoring is like sort of like dividing. It's like taking out the divisors of numbers. And now this 2 over 2 is an interesting number, because 2 over 2, when you have a fraction, every fraction, this one and all of them, every fraction represents the top divided by, every fraction represents, okay, get out of here, represents the top divided by bottom. So that this 2 over 2 is 2 divided by 2, which is equal to 1. And any fraction that has the same thing in the top and the bottom is equal to 1. So this right here is just a 1, and you have the 3 over 2 times 5 is 10. Now, in terms of money, this number is not a whole lot better. 3/10 of a dollar is not much more informative than 6/20 of a dollar. It is a little bit, because a tenth of a dollar is a dime. So you have 3 dimes, so it's 30 cents, which we knew. Okay, so let me do another sort of word problem. These aren't really problems, I'm just playing with the numbers here. So let's say we are going to buy some pencils, and the price of pencils is $2 per 5 pencils. So we had here the word of translated to multiplication. In a similar way, the word per is division. So we have $2 per 5 pencils. And this is not tremendously informative. And you can play with this fraction the way we played with this fraction, all these fractions. So you had a 6 over a 20, and you wrote that as a 2 times 3, and the 20 as a 2 times 2 times 5, and you can split those fractions up using what we know about multiplication of fractions. I can do the same thing here. This is 2/5 times dollars over pencils. So it costs 2/5 of, that would be the multiplication of a dollar per pencil. So you really have a multiplication of and the division per here. So this again, in terms of money, 2/5 of a dollar per pencil is not tremendously informative. You'd like maybe to get that into a more reasonable type of unit, and this is something we'll work on this semester, is units and dealing with units, unit analysis. So 2/5 of a dollar per pencil. If you want to buy one pencil, you'd like to know how much one pencil is. So dollars per pencil, that can help. You can figure out how much 2/5 of a dollar is. Well, in some sense, it's 2/5 of a dollar. 1/5 of a dollar is 20 cents. So 2/5 of a dollar would be 40 cents. But suppose we want to change to cents per pencil. How do I do that? Well, there are a couple ways to go. You could know that $2 is just equal to 200 cents per 5 pencils, so that you have 200 over 5 cents per pencil. And then you can actually perform this division however you would do it. You can do long division. I don't know if they even teach long division anymore. And so you'd get 4, and that would be 20, and 0, 0 is 40, and so you'd get 40 cents per pencil. So you can figure this out. Or if it wasn't a nice number, and I picked nice numbers here just so that they would be, nice whole numbers. But if it was like the price of pencil is $2.57 per 13 pencils, you could do the same thing. The numbers just wouldn't come out all that nice. Now, this is one way to change the units here. I'm going to show you another way, an alternate way to change the units, which is kind of nice because it uses this idea that we just looked at, where if you have the same thing on the top and the bottom of a fraction, you have a 1, so it doesn't matter whether it's a 2 over a 2, or a 5 over a 5, that's equal to 1, or a negative 13 over a negative 13, that's equal to 1, or an apple over an apple, that's equal to 1. Any two things that are equal, if they're in the top and the bottom of the fraction, then that fraction is essentially a 1. Even if those two things that are equal to one another don't look exactly the same like they did here. So like if you want to change units here, we know that $1 is equal to 100 cents. Which means that if these two things are equal, if you put this in the top and this in the bottom of a fraction, that's equal to a 1. And if you put this in the top and this in the bottom, that's equal to a 1 also. So I can use this along with the idea of fraction multiplication to change units. So if I take this fraction that's in dollars per pencil, $2 per 5 pencils, and I multiply it by a fraction that has dollars in the bottom and cents in the top, what happens is I get the 2 times the 100, because now I'm doing essentially for a bunch of multiplications. I have 2/5 times dollars per pencil times 100 over 1 times cents per dollar. And so we'd have the 2/5, because you can do multiplication any order you want to. 100 over 1 dollars per pencil and cents per dollar. And what's going to happen is you're going to get the 2 times 100 over 5 is the 40. Or if you like, you can do the 100 divided by 5 and get the 20 times 2 and get the 40. And now you have dollars in the top and dollars in the bottom. Just like here when we reduced the fractions, we had a 2 in the top and the 2 in the bottom. And it's all multiplication. And so the dollars over dollars are basically a 1. And so we have 40 cents per pencil, which we knew. I mean, we had already done that, just using sort of our intuition that we have, because most of us been working with American dollars and cents all of our lives. So you're probably going to think I'm a little crazy doing unit conversion like this instead of like this. And it is crazy in this case. You wouldn't do it like this in this case because you do have a fluency and intuition with American money. But if you're changing units that aren't as intuitive to you or that aren't so beautiful, I mean, the relationship between cents and dollars is 100 to 1. So those are very nice numbers to work with. But if you're changing something like, say, from feet to meters, those relationships are not going to be so nice. And depending on your background with this stuff, not as intuitive. So this method, it can work nicely. The other thing you can do, I should mention here, is instead of doing the $2 per 5 pencil, it's also 5 pencils per $2. So you'd get 5 halves of a pencil per dollar, which is 2.5 or 2.5 pencils per dollar. So once you have one of these relationships, these per relationships, it can go either way. And so depending on what you're working with and what you want to know. Maybe you want to know how much it's going to cost you for a pencil, so you do dollars per pencil or cents per pencil. Maybe you want to know you have a certain amount of money and you want to know how many pencils you can get. So say you have $1, you know you can get 2.5 pencils per dollar. This is obviously is theoretical. I don't think you can actually buy a half a pencil. So you know, if you had obviously $2, you could get, if you had $2, you could get 5 pencils, which is what the actual original piece of information gave you. Okay, so last thing I want to do, and then I will stop, because I know I've been babbling at you for a while, is just talk about some key facts. Just summarize the key facts about fractions. So, like I said, you have a fraction is a top over a bottom. If your top and bottom are the same, of course you get a 1. And it doesn't matter what the same thing is. Like I said, even if they don't look alike, if they're equal to one another, like $1 equals 100 cents, or even $1 equals 4 quarters. It's the same thing also. So if you wanted to translate from dollars to quarters, you could do that using that relationship. So this means the top divided by the bottom. So if the top and the bottom are the same, or if you did the top and you had the same thing on the bottom, it was the top over the top is equal to 1. Again, regardless of what it is, we did 2 over 2 and negative 3 over negative 3 is equal to 1, and a happy face over a happy face is equal to 1, and a box over a box is equal to 1. I kind of like the box because it means you can put anything in there that you want to, as long as the things you put in the box are equal to each other, even if they don't look exactly the same. You get a 1. Also, another thing that you get from the fact that the top divided by the bottom, the top over the bottom, or a fraction means the top divided by the bottom, is if you take a fraction, a top over a bottom, and you multiply by the bottom, you necessarily get the top back. Now, this is another key thing. So the top over the top, or one thing over itself, is equal to 1. Also, when you multiply a fraction by its own bottom, you just get the top back. And that makes sense from this. If you take something and you divide by another thing and then you multiply by that thing, you've gone around in a circle. So if you have 3/5 and you multiply by 5, what you're doing there is you're taking 3, you're dividing by 5, and then you're multiplying by 5. And dividing by 5 and multiplying by 5, you're doing nothing. You're doing something and then you're undoing it. It's like walking 5 steps forward and then taking 5 steps back. So that's a 3, and it doesn't matter what's in the top and what's in the bottom here, barring like having zeros in the bottom of the fraction. Zeros can cause a little bit of trouble in fractions, and maybe I'll talk about that another time, because I think I've been talking about that enough. Okay, very good.